All right. So, where we left off in our notes, we had just talked about how we estimate population size and why it's important. Today, we're going to look a little bit at some of the conditions under which populations grow, and then also how we can calculate how quickly they're growing. Okay. So, if you already read the textbook or watched the podcast, you should know that there are two main types of population growth. We have exponential growth, and then we also have logistic growth. Okay, those are going to be the two models of growth that we're talking about today. We also have several equations that we can use to calculate population growth under those two different conditions. So we have our overall equation for population growth, and it basically says that the change in population size during a specific time interval is going to be equal to the number of births. And then sometimes we're also going to include the amount of immigration. So how many new organisms are coming into that population, okay, in whatever that time interval is, minus the number of deaths. And then if we're including immigration, we're also going to include emigration. So the number of individuals or organisms leaving the population over that time period. Okay, so we should know immigration, and emigration are not always included, but we are always going to include our number of births and our number of deaths. Okay. Now we have a couple of different ways that we're going to see that. Sometimes you can just do births minus deaths, but we're also going to see that in a few other ways. Okay, so what you're often going to see is the change in N, which is going to be our number of organisms in our population, over our change in time, all right, is going to be B minus D. So that's basically what we just wrote up there. But what we also tend to see is the change in the number of organisms over the change in time, okay, is going to be equal to R times the number of individuals in the population. So that R is going to stand for our per capita rate of increase, okay? And I'm going to tell you how to calculate that in just a second. But before we do that, let's go ahead and write down what all of these things mean. So again, that delta N, that's our change in the population. That delta T is going to be our change in time. That big B is births, big D is deaths, okay? And then our R is going to be our per capita, so per individual rate of increase. Okay. We can calculate the per capita rate of increase by using this equation here. So R, right, that per capita rate of increase is going to be equal to the number of births minus the number of deaths over the total number of individuals in the population. Okay, so R can equal B minus D over N. Okay, it can also equal, if you get a birth rate, so little b is going to stand for birth rate minus m, okay? And that is going to be minus the death rate or the mortality rate for that population, Okay, so those are going to be the big equations that we're going to use. We're going to finish writing down, though, all of the what all of those letters actually symbolize. Okay, so little b is going to be our per capita birth rate. So what's the overall birth rate per number of individuals in our population? And then that little m is going to be the per capita death rate or the mortality rate. And then depending on the resource that you look at, sometimes you'll actually see that M symbolized as a little d for death rate, okay? Okay, so let's do a quick example before we move on. So if we have a population size of 1,000 and during a certain time period, 200 offspring are born and 100 individuals die, what is the growth rate? Okay, now when we see that word growth rate, we should know that we're looking for R. That's our per capita rate of increase. Okay, so not the number of individuals being added, but the rate of individuals per capita. Okay, so we know that we're also given the number born, so a big B, and the number that die. Okay, so that is going to be a D. And then we're also given our population size, and that's going to be our N. Okay, so looking at everything that we're given and looking at what we're solving for, we know that we can use R equals B minus D over N, and then just plug in the numbers that we're given. Okay, so again, 250 minus 100 over 1,000, and that should give us 0.15, okay? Or you can think about that as being a 15% rate of increase in our population, okay? So those equations that we just used are going to be really well suited to explain exponential growth. So that's what we're going to talk about next, okay? So exponential growth is going to describe the growth of a population that is growing rapidly with no limits to resources, okay? So I'm going to write, it describes populations that are growing under ideal conditions. And when I say ideal conditions, I'm meaning unlimited food, unlimited resources, unlimited reproduction. Okay, so they're growing under ideal conditions and increasing at a constant rate. Again, we want to think about this as a situation where there are unlimited resources. So no limits to the resources in our population. Okay, so some examples of populations that might be growing in an exponential growth kind of condition would be something like weeds in a garden, right? They can outcompete the things that are there. Maybe invasive species, so species that are non-native and don't have their natural predators or things like that that are just being established in a space, so invasive species. Sometimes if you think about maybe like a newly protected endangered species where they were being hunted or something before, but now those limits have been kind of taken away. Those would be a good example as well. And then you can also think about bacteria. That's not how you spell endangered. Bacteria growing in a lab, that would be another kind of condition where those bacteria have ideal conditions and can kind of reproduce really, really quickly. Okay, so here we have our graph. So we're just going to talk really quickly about our equation one more time and our graph. Okay, our equation is the one that we just talked about. So the change in our number over the change in time is equal to the rate of increase times the number of individuals. When we're looking at this, in our graph, what we're going to see is that R is going to be constant. And then we're going to see that our N is increasing exponentially. When we put this on a graph, like we have over here, we can see that our graph is showing a J-shaped curve. Okay, so one of the things that you're going to look at is you're going to look for that J-shaped curve where our population growth is growing faster and faster and faster as the population gets larger and larger and larger, right? Because as our N to begin with gets larger, right, we're going to see more rapid growth when we multiply it by that R. Okay, so here at the very beginning, we're going to have a really, really slow growth. We have what we call an establishment period, where the organisms are just being established in that population. And then as our N gets larger and larger and larger each generation, we're going to see faster and faster growth. So more and more individuals added to the population over that period of time. Okay. Now, exponential growth is not super realistic for normal populations. We usually in nature don't see this occurring for very long because we do have unlimited, or we don't have unlimited resources, okay? So that's when we start talking about our logistic growth model. And this is going to be the growth type where we are taking into consideration limiting factors or limited resources, okay? So logistic growth is going to be, I'm just going to say this type of growth takes into consideration those limited resources or our limiting factors. Okay, we actually have two types of limiting factors. This is an important vocab term from our chapter. We have density dependent limiting factors. Okay, and those are going to be the limiting factors that are going to see a larger impact as the population gets larger. So what you can kind of think about is that the mortality rate is going to increase, and maybe even the birth rate is going to decrease with rising population density. Okay, so if you think about things like food, shelter, availability of mates, those are going to be our density dependent limiting factors. Okay, we also have density independent limiting factors, and these are going to be the types of limiting factors that affect all size populations in the same way. Okay, so this kind of situation is usually going to be something like there are floods or droughts or some type of habitat destruction caused by another population or even by humans. And what that's going to do to all of the populations, regardless of that size, is it's going to limit the size of the population. So we can kind of think about this as saying the birth rate or the mortality rate, death rate, they do not change with rising population. Or population density, I'll say. Okay, so affects all size populations in kind of the same way. Okay, now our limiting factors are what actually determine something that we call our carrying capacity. Okay, so another way of saying that is that limiting factors determine how many organisms an environment can support. Okay. That number of organisms that our environment can actually support is what we are going to call our carrying capacity. Okay. So I'm just going to write this number is called the carrying capacity, and carrying capacity is actually something that we're going to start to pop into our equations. And when we do that, we are going to symbolize it with the letter K. Okay, so now instead of using that original equation that we had used before, okay, so C is going to be our equation slash our graph, we are going to say for our equation that the change in our population size over the change of time is still going to be per capita rate of increase times the number of organisms in the generation. But now we're going to multiply that by an expression that takes into account our carrying capacity. So we're going to say K, again, that's our carrying capacity, minus N over K. So we're going to multiply our original equation times the K minus N over K. Okay. So again, K is carrying capacity, and that carrying capacity is going to be determined by limiting resources. Okay, so carrying capacity is not a static number. It can change over time as the resources actually change over time. Okay, we're going to get into our graph in just a second, but before we do, we can kind of think about some situations that we typically see. Okay, when our N, or the number of organisms in our population, is small, typically that means our per capita rate of increase, okay, is going to be pretty large. As our population size gets closer to the carrying capacity, that growth rate is typically going to get smaller and smaller and closer to zero. Okay. So if we look at our graph here, we can see that it looks a little bit different than the graph that we saw for exponential growth. Instead of having that nice J-shaped curve, we have what we're going to call an S-shaped curve. Okay. And we have kind of three different parts that we can identify on our graph. The first is that establishment period. We did talk about that with our J-shaped curve as well, but we didn't write it down. So our establishment period is when N is small, so our population size is really small. So what we see is slow population growth, right? The larger our population is, the faster it typically grows with the same per capita rate of increase. And then here, number two, this like area that we labeled number two here, that's where we see that really, really high slope. The higher the slope, the faster the rate of growth. Okay, that is going to be our rapid growth period. Okay, oops. And actually we see for a little bit that first part looking like that J-shaped curve from our exponential growth. So we're just going to label that our period of exponential growth. Okay, that's where we have rapid growth again, with N being fairly large, getting larger and larger. And our R at that point is still pretty large. Okay. And then that very last portion of our graph, if we're looking right over here, okay, is going to be where our population is nearing like almost a zero growth, okay, um, as we reach that carrying capacity. So we can see that kind of period or that spot on the graph where our population's kind of hovering around that. We labeled it K on our graph. Okay. That's our carrying capacity. That's where those limiting resources are starting to affect our overall rate of increase. Okay. Our N is still large, but the R is small. Okay. And one thing to kind of think about is we usually in a population, we don't see it reach the carrying capacity and stay there. There's often a little bit of an overshoot and then kind of a hover around that carrying capacity, dipping a little higher, a little lower, but kind of hovering around that space. Okay, so I know that I wrote here R is large, R is small. One thing to kind of keep in mind for your R is that when you think about R being greater than zero, that means that we have a growing population. When R is less than zero, that means that we have a decreasing population. And when R is equal to zero, that means that we have no population growth or zero population growth. Which we can just kind of abbreviate ZPG because our population size is staying the same. Okay, so now that you've kind of seen everything you need to do, what you're going to do is you are going to go to Schoology and you are going to download these population growth rate calculation practice problems. So the first two examples, pretty simple, just like what we did in the notes. I know we didn't do an example of the logistic growth. Only thing that changes there is the addition of your carrying capacity, okay, which again is going to be the K in your equation, okay? So remember, our change in our population size is going to be equal to Rn K minus N over K. So that's the only thing that's really changing in our population, okay? From there, you've got a couple more examples. You're going through, you're working through it. And then you have just like a mixed set of problems. The only thing that I think I forgot to add on here is your population density equation, but you have that on page 1 of your notes, okay? So work through it, do the best you can, and when I'm back tomorrow, we will go through everything. It's going to take some time, but once you get the hang of it, it should move pretty quickly, okay? Write down any questions you have, and I will see you tomorrow.